Right, we're on video 9 for Math 2210. We are going to talk about two questions relating to applications of Green's theorem for finding a circulation of contours through vector fields. So our first question says find the circulation for f given by x over 1 plus y squared times unit vector I plus inverse tangent of y times j around the circle of radius 1 centered at 0. And it says to run through this path counterclockwise. All right, so first of all, let's remember what we mean by circulation. So recall, circulation is just a work line integral through some closed curve C. Okay, so that's what we mean by circulation. It's just a work or line integral along, and for it to be circulation, it must be a closed curve. In other words, that it has to somehow be connected, the whole line there. We'll look at how this is closed in our example. A closed path, we call it C. So that's what we mean by circulation. All right, so in our case, what is C? Well, they tell us that we're going to go around a circle of radius 1 centered at the point 0, 0. So let's just draw a picture of what this is going to look like here. So what is C? Well, it's this, I'll use another color here. We're going in a circle that is of radius 1 around the origin here. And they said that we're moving in a counterclockwise direction, right? Okay. So we found that that's what our the path that we're going over. Now, you could do this line integral by hand. It might be a kind of difficult to do the parameterization kind of like we did in the last video and go through all those steps. But we're going to use Green's theorem to calculate this. So let me just write down what Green's theorem is, and then I'll talk about the different parts that we are going to need to get from the picture here in order to set up the problem properly. So first off, remember what Green's theorem says. Green's theorem says that if I want to calculate the line integral along a closed contour, right, and this is just regular line integral as before, then this is equal to the region R. Well, we'll talk about what that region is, of the curl of F over the area there. All right, so this region R, actually R here is the region to the left, as we move through C. Okay, let me explain what that means. Move along C. All right, so if you were going to walk along this curve right here, the region R is the area or the little region that is to your left if you're walking along the path or the contour. So in our case, this is the region R. It's the inside of the circle, right? That's the region R. Okay. Right, now we need to talk, so this is our Green's theorem. Our region R is the inside of the circle. Let's talk about what we mean by curl. All right, so this is something I think that has been talked about in class, but let me just remind you, in case you forgot, for a function that is two-dimensional, so for a 2D vector function, vector value function, maybe we say that it looks something like this. F is of the form m and n. right? It has those two components, or maybe like we have it in our case, it's mi plus nj, right? Looks something like that. Then the curl, or maybe in your textbook, I think it uses this notation, the gradient cross this vector f. This is equal to the partial with respect to x of n minus the partial of m with respect to y. Okay, so that's what we have for the curl. So let's go ahead and calculate it for our function f. All right, so let's apply Green's theorem to solve our problem. All right, let me just come down here and give myself some space. Okay, so we are interested in solving this problem right here, where our C is the circle. I'm just going to draw a picture of the circle to remind us that that's what that is. And the f is the function they gave us above, that x over 1 plus y squared I plus arctangent or tangent inverse yj. All right. So we apply Green's theorem, and we get this is going to be over the region R, which is the inside of that circle. We'll figure out how to write the limits of that in just a moment. But let's go ahead and shove in what the curl is here, right? The curl for our situation, if I'm going to take the derivative with respect to x of this n part, that means I have to take the derivative of arctangent with respect to x. So that's going to be the partial with respect to x of tangent inverse of y minus, now it will be the partial with respect to y of the other guy, right, which was x over 1 plus y squared, right? This is equal to, if I take the derivative, well, that's just a constant with respect to x, right? So that will be 0 minus, this x is just a constant with respect to y, so that will be x over 1 plus y squared. Now I decrease the power, so it goes from like 1 plus y squared to the minus 1. Now it's going to be minus 2, but it's in the denominator, so it will be squared. And I will actually pick up a negative 1, right, from the power rule. And from the chain rule, I pick up a 2y, right? Or no, just a y, I think, right? Because this is actually, hold the phone here. Right, it's a 2y. Perfect. All right. So this is going to be 2yx over 1 plus y squared, the quantity squared. All right, there we go. Okay, so now we can shove this into our, let me just move this stuff down a little bit out of the way now so I can not get confused. This was the curl, right? Remember, this is what we calculated to be the curl of f. So if we shove that in, according to Green's theorem, this will be 2yx over 1 plus y squared. This guy squared. And then we'll just leave it as dA for the moment. And then we know how to parameterize these things. Hopefully you've kind of got comfortable thinking about how to write the limits of this. If not, let me just draw the picture of here really quick so we can just remember. This function here, if I wanted to draw the circle, if I wanted to write out what the circle is going to do, I might write this right-hand side as being something like x equal 1 plus y squared, and the other one is being x equal negative 1 plus y squared. If I wanted to go in that direction like that, right? This would represent the guy over here. This represents this half, right? So maybe I do this color. This color goes to that part. This guy is talking about him. All right. So let's go ahead and set, and then of course I'm going to go in the y direction from -1 to 1. All right. So it will be -1 to 1 of integral. I will go starting from maybe the negative part, 1 minus y squared. Oh, that should have been a minus on those. Sorry about that. All right, because it's x squared plus y squared equal 1. So that means that x is equal to the plus or minus the square root of 1 minus y squared. Sorry about the confusion on that. Okay, so right, that's a negative 1 minus the y, and this is going to be 1 minus y squared there. And then I integrated first with respect to this guy is with respect to the x's. So I will have a dx, and then the last guy was with respect to y, and then my inside part here will just be the same. All right, you might be looking at this integral and say, oh, yikes, you know, this looks pretty bad. Let's just think about it for a moment. This inside part, if I'm going to integrate it with respect to x, this whole bit right here is just a constant, right? It's constant with respect to x. So let's just think about it. If I have a constant, right, let me just look at the inner integral for a moment. And I'll just kind of think about it in a generalish way. If I want to, the limits here are just, let's call this guy a and this guy, if this is a, this is just negative of that guy, so this will be negative a, right? So I could think of this as being the symmetric interval, right, from negative a up to a, of this guy, that's just a constant, so why don't I just call it c for a minute, and then this variable x with respect to x, right? Okay, perfect. So what will this guy turn out being? Well, it's going to be cx squared over 2, right? And I evaluated around that interval that's symmetric. Well, notice what happens. This guy is actually 0 because I get a squared over 2 minus a negative, right, a squared. So that's going to just be the minus a squared, just goes to a squared over 2. This is just c times 0 is 0. All right, why did I take the time to do that? Because it shows me that this inner integral, right, is actually 0. Right, so I don't have to continue doing any calculation now. I know that this guy, right, is going to be exactly 0. That will be the answer, right? The integrating again 0 will do me no good, and integrating 0 from -1 to 1 will just give me 0 again. So, right, perfect. That's the answer there. That is this the circulation around the center of that, around the circle of center 0, radius 1. All right. All right, let's go ahead and take a look at the next question. It's kind of similar. We just have a different function and a different region, but in the similar way, we're going to apply Green's theorem. This question will actually go a little bit quicker because we notice something really nice happen. So let's go ahead and look at this. So I'm interested in finding circulation, which we decided was this line integral, right, along this closed path. So the closed path means that it's completely, I can just keep walking around and around it, like water could flow along that or something. Maybe that's where they get this idea of circulation. All right, this is going to be over the region R, which is this guy in here. Remember the stuff that is to the left as we walk around the contour, or as we walk around the path of the curl of f, right, with respect to a. All right, now let's go ahead and calculate what is the curl. Okay, that is going to be this derivative of the first guy, or the second guy, with respect to x, right? So that will be 1/2 times 3, or times 4, excuse me, right, 4x cubed y minus the derivative of the first guy with respect to y. So that will be 2yx cubed, right, and that, I guess we leave it as dA. Why not? We don't have to think about which order we're going to put the limits, because look what happens. This guy is actually 0. Right, let me just write it so it's a little bit more obvious. If I simplify this up, this is 2x cubed y minus 2x cubed y dA. Well, that's 0. Okay, pretty nice, right? It doesn't matter what path I take through here, though. The curl, or this guy right here, the integrand here, is always going to be 0. So this is actually a special property of f, which is, or of this vector field. We say that f is conservative. If it doesn't matter what path I take through the vector field, I always get the same answer. All right. Well, hopefully that helps you with your homework problems. This is that'll be the end then.